Alright, so in this lecture we're going to look at the quaternions and how they can be used to derive the foursquare theorem. This is based on Chapter 8 of Stillwell's Elements of Number Theory. To begin this lecture, I'll just remind you how we can build the complex numbers from 2 by 2 real matrices of the form AB minus BA. And so if you work through the math of that, when you multiply two such matrices, you get the matrix of the product where we multiply, A plus BI times C plus ID as you'd expect in terms of complex multiplication, right? So in other words, these 2 by 2 matrices multiply in the same way that complex numbers multiply. This gives us what you might call a model of the complex numbers as 2 by 2 real matrices of this particular form. And so in addition, if you look at the norm of these 2 by 2 matrices, well, the norm is the determinant of the corresponding model matrix. So that if you take this approach, then to derive the multiplicativity of the norm, it just becomes a consequence of the determinant of the product is the product of the determinant's identity, which is kind of slick. Obviously, this is not how I did it in the previous lectures. In fact, I never really explained to you why it is that the I used the fact that the conjugate of the product was the product of the conjugates, and you both agreed that that had been proved in previous courses, so we didn't get into it. But here's a more complete proof, actually, in some sense, that the norm of the product is the product of the norms. Okay, so are complex numbers really 2 by 2 real matrices? Well, I wouldn't necessarily say that. There are actually a number of different ways you can construct complex numbers, and this is just one of them. So I have more of the school of thought that complex numbers what that means is you're working with a formal system which is a lot like the real numbers, except you've adjoined an element that we call I, which has the squares to -1. And just to be brief about it, and multiplication and addition behaves normally. There are you could be more formal and develop a system of axioms and so forth, but I don't think of the complex numbers necessarily being this 2 by 2 matrices, but it does give me confidence that there exists a set of elements which has the properties of the complex numbers in the way in which we talk about them, right? So next up, I will show you a model, all right, of the quaternions. And to build the quaternions, you can use 2 by 2 complex matrices. Now you're probably like, what are quaternions? Well, we'll hang with me here for a second. So a quaternion, to start with, is going to be a 2 by 2 complex matrix, alpha beta minus beta bar alpha bar. So it's got a complex number and its conjugate, a complex number and minus its conjugate on the off diagonal, like that, right? And if you multiply two such things, you get a new matrix, which again has that same format. See, this is the 1 1 spot and the 2 2 spots are related by conjugation. The 1 2 and the 2 1 components are related by conjugation and a minus. So in other words, when you multiply two matrices of this form, you get another matrix of this form. All right, so the multiplication's closed. So definition, if we have such a quaternion 2 by 2 matrix, then the norm of Q is going to be the determinant of that. So that's my printer is not quite making it here. I'll have to fill in some of these. So the norm is just the alpha alpha bar plus beta beta bar, right? In other words, the norm of Q is the magnitude of alpha squared as a complex number plus the magnitude of beta as a complex number squared, all right? So, for example, if alpha was equal to, let's say, A plus IB, and beta was equal to C plus ID, then this would literally be A squared plus B squared plus C squared plus D squared. So perhaps you can start to see why maybe this has something to do with a foursquare identity, all right? So moving on here. Since we use matrices to define the quaternion algebra, we have some very natural properties like associative, right, distributive, both ways. The norm is multiplicative because of the determinant. The product is a product of the determinants. However, just like matrix multiplication is not commutative, these quaternion multiplications are not commutative. It just so happens that the previous thing I started lecture with, it's, you know, these are these guys, these are special. These kind of matrices commute with these kind of matrices. So this is actually commutative, despite the fact it's using 2 by 2 matrices. So, just saying. It is possible to model commutative algebras using matrices. But anyway, so we're looking at H as 2 by 2 complex matrices. It may be worthwhile to remove some of the weirdness of H, but in practice, the notation is what is preferred for. The notation which follows here is preferred for applications of H. Similarly, we use A plus IB rather than this 2 by 2 matrice as we study complex numbers and anything other, in all other courses, right? So, let's see here. So a good notation for H is, instead of using this 2 by 2 matrix, we'll call this one 1, we'll call this matrix I, we'll call this matrix J, call that matrix K. So you notice that I times I, J times J, and K, hey, where it is? Well, K, I'm missing, but also K times K is equal to minus 1 as well. And by minus 1, I just mean the matrix minus 1, 0, 0, minus 1, all right? So 1 here literally means this 2 by 2 matrix in this way of thinking. There's, of course, a danger of ambiguity here because I'm using 1, and I mean different things by them, but anyway, it is what it is. As much as I hate when people say it is what it is, I find myself doing it. Sad, sad, sad. Anyway, so I times J, multiply these, let me scoot this up a bit. I times J, when you multiply these, you get K. J times I, you multiply these, you get minus K. And so, you know, in summary, if you work out all the relations between this I and J and K matrix, what you're going to find in summary is that I squared equals J squared equals K squared equals minus 1. Ij is K, which is minus Ji, Jk is I, which is minus Kj, and Ki is J, which is minus Ik. This is the algebra for the imaginary units, I, J, and K in the quaternions. So I think the truth is that when Hamilton found these quaternions in the early 19th century, well, mid-19th century, he did not invent them as 2 by 2 complex matrices. No. What Hamilton did was to invent, he just said, well, suppose you have, you know, in R4, 4 real dimensions, and it has this particular algebra. And he just basically wrote down a multiplication rule that is really codified by these relations right here, and probably set aside the question of whether or not such a model exists. I mean, typically people worry about existence later. I think it's less likely to have been a concern of Hamilton. I mean, the existence is kind of, it's nearly automatic if you can come up with an algebraic system which is consistent. But the reasons for that I shouldn't talk about here, so I'll leave that for another day. But anyway, basically, the quaternions is it's a real number, and then you would join the real numbers, imaginary units I, J, and K, but they don't commute. They have to satisfy this kind of funky algebraic rules. But if you look at these, they're actually kind of totally natural, right? Because calculus 3, cross product of I and J is K, right? The cross product of J and K is I. The cross product of K and I, J and K is I. Cross product of K and I is J. And the cross product is anti-commutative, right? So these rules are not surprising from the perspective of the cross product in 3 dimensions, but you must remember the cross product in 3 dimensions was not known widely, at least at the time of Hamilton. So, like, you know, that's something that was discovered after the quaternions, actually, that way of thinking, the school of vectors, as promoted by Gibbs and such. So there was actually a time period, probably about 50 years, where quaternions held the same sort of prominence that vectors do today. So here's a more formal introduction to quaternions. This is how I would typically teach it if I did have more time. I say a quaternion has the form t plus xi plus yj plus zk, and we can say the real part of the quaternion is t, the imaginary part is this piece, xi plus yj plus zk, and we have to assume these identities, all right? The conjugate is real minus the imaginary, and the quaternion's real if only if the imaginary part is 0. It's pure imaginary if and only if the real part is 0. And the norm of a quaternion is the product of it and its conjugate, which turns out to be t squared plus x squared plus y squared plus z squared. That's rather beautiful and in tune with what we wrote in the complex number system, right? But this is not a commutative system. It's a non-commutative system, and yet it shares so many commonalities with commutative number systems. It's very special. I've often heard it said that the quaternions are just barely off. So they're so much like things we're used to, and yet they've got this just slight twist of things. Anyway, so alpha 1, alpha 2, if we have pure imaginary, we multiply this times that, you distribute out, so then you got your I squared, your j squared, your k squared, those give you minus 1s, so you get this guy, and then the ij and the ji give you the k term, the ik and the ki give you the j term, and the jk and the kj terms give you the I term, and sorry, L, z1, x2, x1, c2. This is fine if you look at the, this is just my printer. The PDF scan of this is just fine. And it's it's linked on my web page for number theory, which I have linked at the top of my web page, so you guys should know that. But anyway, look at it. So what we have is the multiplication of two pure, I'm going to zoom out just a bit because otherwise we're not going to quite fit these formulas. So the, see, there's the end of the universe for me now. Move my block down. There we go. Let me keep track of what you guys can see. So, so if you look at this, the product of two pure imaginary quaternions, it gives you the dot product with a minus and the cross product if we think of these as vectors. So the quaternion multiplication has both the dot and the cross product in it all at once. All right. So that's about 50 years before vector notation took over. So if we look at quaternions which don't have just imaginary parts, which also have real parts, multiply those, it's a little bit messier. You get the product of the real pieces, the product of the the pure imaginary pieces, and then this piece over here. And so, as I said, we have calculated this alpha 1, alpha 2 in the previous page. So we know that alpha, when we take alpha 1 equal to alpha 2, and we calculate the product of alpha and alpha bar. So what I'm doing at the moment is proving to you that the formula really does work out to t squared plus x squared plus y squared plus z squared. I claimed it in the previous page, but I didn't really show it yet, and here I'm showing it. So t plus alpha times t minus alpha is the conjugate, right? And so you expand that out, the t alpha and the alpha t alpha and the minus t alpha cancel, and the alpha alpha, well, that gives you minus the dot product of alpha with itself. The cross product of any vector in itself is 0, so that's gone. So you get t squared plus alpha dot alpha, but alpha dot alpha is, of course, the length squared of the vector alpha. Therefore, there it is. Now, once you know, so let's see here. So I have claimed a lemma, apparently. Oh man, I need to keep my reminder where my. All right, so the norm of the product of two quaternions is Q1, Q2, Q1, Q2 bar. Keep in mind, guys, that quaternion multiplication is non-commutative. So something funny happens. It turns out that the quaternion, the conjugate of a product of two quaternions, is the product of the conjugates, however, in opposite order. So that's kind of interesting, but that's actually very important here, because see what happens is they flip-flop, and then you got Q2, Q bar, well that's the length of Q2 squared. Now that's a real number, so that just pulls out, and then you get Q1 and Q1 bar, which is the norm of Q1 bar norm of Q1 bar. So there it is, the product of the norm of Q1 and Q2. You can write them in the opposite order, right? These are real numbers. So I said I'm going to leave the lemma to you guys. Hey, I think I just found a homework problem. Woohoo! All right. That's actually a pretty. That's exactly the kind of homework problem I want to give you guys. I have no intention of giving you homework problems on the second half of this lecture, because this is the easy part. Anyway, so what's the foursquare identity? Well, here it is. The norm actually, this is the foursquare identity. The fact that the norm of Q1 times the norm of Q2 is the norm of Q1, Q2, that actually is the foursquare identity, but let's unpack that. So the norm of Q1 would be like A1 squared plus B1 plus C1 squared. So I'm saying, just to be clear here, guys, I'm saying Q1 is like, A1 plus IB1, come on, plus JC1 plus DC1, KD1, and Q2 is A2 plus IB2 plus JC2 plus KD2. So I'm saying these quaternions are Q1 and Q2. All right, they have these four real components, A, B, C, D, numbered 1 or 2, respective to Q1 or Q2. And so, lovely. And the norm of Q1 is this, the norm of Q2 is that. So you can multiply those, right? But on the flip side of things, it's the norm of this squared, right? And so you can multiply out Q1 and Q2, and when you do that, you get this. All right, so like multiplying this, well, so I'm just distributing, right? See the 1, the I, the J, the K, and let's see here. Well, I'm distributing this multiplication, I'll just say that. And then if I multiply the I through and I multiply the J through, what happened here? Oh, I'm sorry. I'm being too optimistic. I have not shown that much work. It is a straightforward but tedious process to multiply these two out to get this. All right. That actually would probably make a good homework problem for you guys. Hey, what do you know? Seems to be a theme here. Anything I'm missing, I'll make into your homework problem. But anyway, here we go. And then the norm of this, well, it's this component squared plus that component squared plus that component squared plus that component squared. And so you have this rather formidable algebraic identity. The sum of these four squares is equal to the product of the sums of these four squares and these four squares. This is the foursquare identity. Who found this? Euler. All right, Euler found it in 1748 without the help of the Quaternions. And Euler wanted to prove all natural numbers were expressed as sums of four squares. And it turns out that Lagrange did it in 1770. And we'll give the proof in the second part of this lecture. Kind of, I'll sketch it at least. But anyway, it is, which mirrors? Oh man, come on. Mirrors. Mirrors. There, that's the word I'm looking for. Mirrors are proof of the two-square theorem, built with the structure of the Gaussian integers. Oh, man, who wrote this? Oh, so there you go. So that was a brief introduction to Quaternions. And of course, Quaternions, they're a very interesting number system. There is a loyal fan base for Quaternions. People advertise, oh, you can do better computer programming with Quaternions because the gimbal lock and the other thing and whatever, I don't know. I've got nothing to say about all that. I have tried to understand how to implement rotations with Quaternions, and I feel like it's a black hole of mathematics. It's not that complicated, but just not talk about it. All right, so to apply complex numbers to the two-square problem, right, we had to look at not all the complex numbers, but the complex numbers with integer coefficients. So the first thing you might try would just be like, the integers with extended by I, j, and k. All right, but the thing is, this is a lot like the z adjoint square root of 3 that we talked about last time. It's too sparse. like it's too spread out, so the division algorithm is not going to hold. But it turns out that if you throw in the half integer ones, all right, you throw in these guys, then your fundamental cell is small enough that it works out. And if you take the integers and adjoin 1 plus I plus j plus k over 2, as well as I, j, and k, this dreadful algebraic system is known as the set of Hurwitz integers from 1896. Fun fact, the sum, difference, and product of Hurwitz integers are Hurwitz integers, and the norm of Hurwitz integers is an ordinary integer. I'll show you the proof of that next page here. So, I mean, here's a sample example one. So if I take 7 plus I plus j plus k over 2, so that's, you know, I plus j plus k over 2 plus 3. Well, the norm of that is 49 plus 1 plus 1 plus 1 over 4, which is 52 over 4, which is 13. Yeah, but anyway. So, oh, by the way, that makes this a Hurwitz prime for the usual reasons, because its norm is prime. So that's still going. All right. So, just a second here. I need to get my cover sheet to help kind of control the flow of information here. Hey, maybe I could work for the government. Let's see here. So the norm of a times 1 plus I plus... I should come up with a name for that thing. Anyway, the a times 1 plus I plus j plus k over 2 plus bi plus cj plus dk, I'm claiming that that's an integer. Here's why. If your quaternion is such a thing, right, then the norm of the quaternion is the length of the quaternion squared, which is this, right? So, well, to see that, the only real component here is a over 2. That's why I have a squared over 4. How about the I component? Well, I've got a over 2 plus b, right? A over 2 plus b squared. I've got an a over 2 from this j term, and that adds to c. I've got a k over 2, which adds to the d, so I get a plus d over 2 squared. Then I do what? I factor a quarter out, like so. Then I factor the quarter all the way out, like so, and I rewrite those. Lovely. But then the thing is, these are odd. Wait a minute. 2d plus, how do I know they're odd? I know they're odd. Well, I said if a is even, then a squared, oh, then these are all even, right? And their squares are in 4z, right? Well, the point is, if a is even, this is the inside of that's even, the inside of this is even, the inside of that's even, and when you square an even thing, you get a multiple of 4, right? So if this is all a multiple of 4 and you divide by 4, bingo, we got an integer, right? So there's that case. On the other hand, if a is odd, right, then a squared is also odd, and likewise every one of these is odd, right? And when you square odd, you get odd, so odd, odd, odd. So we've got odd plus odd plus odd plus odd. And think about how that goes. But it's not just that. The odd square has a 4, multiple of 4 plus 1, right? Let me just scan down here a bit. This is a lot like a homework problem I gave you guys. Probably if I remember the homework problem, I could just cite it and be done with it. But anyway, when you square odd integers, you get this, you know. And so when you add 4 of these together, you got things that are multiplied by 4 plus 4. So 4 divides the sum of 4 odd squares is the point of it. Which is then proving, of course, that the quaternion norm of a Hurwitz integer is in fact a integer, which makes Hurwitz integers interesting because they have a norm which is integer, positive integer, or I guess it could be 0 if it's 0 valued. So this claim was crucial for the reason that quaternion in the Hurwitz integers is has the norm of q, which is a ordinary prime. All right. So, and I claimed before that if the norm was an ordinary prime, that implies q is a Hurwitz prime. That was that only made sense if this was true. All right, conjugates. So in lecture 14 we already discussed conjugates. In other words, in the earlier part of this lecture we already discussed conjugates. And properties of the conjugate by your homework problem, same but in reverse order. The conjugate of sum plus or difference is the sum or difference of the conjugates. And so, in any event, here it is. If p is a prime in the integers, but not in the Hurwitz integers, then p is the sum of 4 squares. This is much akin to the result we had in the Gaussian integers, which said that p is a prime in the integers, but not in the Gaussian integers if p is equal to a squared plus b squared, right? But, ooh, a little bit more. Look at this. 2a, 2b, 2c, and 2d have to be integers. So, that's interesting. So a, b, c, and d have to be like half integers, which means they could be integers if the, you know, how to say, 4 over 2, you know, that's still 2. All right, I shut up. Anyway, here's proof. And I am not suggesting you write all these proofs down. I have no intention of really testing you on these. I'm just going to give you a, you know, I will test you on the larger story here, probably, less than the details. So anyway, here we go. So try to stay tuned for the larger story I'm telling. So suppose you got a prime. In the, let's see here. Suppose p is equal to a plus bi plus cj plus dk times gamma in the Hurwitz integers. And I'm supposing p is prime in z, right? But and I'm supposing then that p is composite in the Hurwitz integers, right? Like this. Then conjugate gives you that, right? And so when you calculate p squared, that gives us the product of this and that, which you get the length of gamma squared, whatever that is. Remember that the length of gamma is assumed to be larger than 1 here because we're assuming it's composite. And you get a squared plus b squared plus c squared plus d squared times that. But p is prime, and you know this is larger than 1, so that implies that you must have a squared plus b squared plus c squared plus d squared equal to the prime. Maybe it would be helpful to write this instead of gamma, because you're tempted to think this is a square, but really you should think of this as like norm of gamma. So you see you've got the product of two integers that's equal to a prime squared. It must be that this is a prime and that's a prime, because both of these integers are larger than 1. All right, so it forces the sum of the squares to be equal to p. And then finally the little claim about the 2. If a, b, c, d are in 1/2 z, right, then 2a, 2b, 2c, 2d are in z. And so that's the format of a Hurwitz integer is that a, b, c, and d are half integers. So this is assumed by saying a plus bi plus cj plus dk is in the Hurwitz integers. All right, what's this remark down here? We showed in lecture 14 that that's true. Hence, this is true. So the norm of z is the norm of z times zw is the norm of z times norm of w. Thus, p equals to that implies norm p is norm this times norm gamma. We've derived this again here. Oh, okay, yeah, fine. Some of my remarks are interesting. Some of them are not. Okay. Anyway, an ordinary prime p, which is not a Hurwitz prime, all right, is the sum of 4 integer squares, claim. All right. Isn't that what we just proved? I thought that's what I just proved. P is a prime in Z, which is not a Hurwitz prime. I thought that's what I just proved. Well, I am most confused. Well, let's see if this is actually different. I don't know. Let's see if alpha, I'm writing it as omega plus a prime plus b prime I plus c prime j plus d prime k. omega. All right. I don't understand why this is here. I must be missing something. Yeah. Uh-huh. Okay, well, you know what? Whatever. All right, so prime divisor property. Stillwell claims section 8.5 contains proof of the division property for this. Yeah, I don't see it there. Let me attempt the proof. Oh no, what am I doing? This sounds bad. So I'm attempting a proof of the division property for Hurwitz integers. So in particular, for alpha, beta, non-zero in Hurwitz, there exists a quotient and a remainder Hurwitz integers for which alpha is mu beta plus rho, where the norm of rho, of course, is less than the norm of beta, the dividing quaternion. So I said almost a proof. Well, that sounds like me. Let's see here. So almost a proof. I said notice a quaternion, as well as Hurwitz multiples of beta, fill the space of quaternions in some four-dimensional lattice. So alpha over beta is some quaternion. Hence, there exists some closest point in the Hurwitz integers, which is to say, z is an element of the Hurwitz integers. So alpha over beta minus z is less than 1. That's my jump. Okay, and so alpha over beta is equal to this for some choice of so here's the closest point, I think. Wait a minute, no. Sorry, thinking. So I guess Q1, Q2, Q3, Q4 are rational, all right, but we can choose a half integer A, B, C, D such that we're within 1/2 a unit for each of them. And if you could actually prove the jump, you set rho equal to alpha minus z beta, and then you can check that if we put mu equal to the z that we picked, the closest thing to the closest point in the Hurwitz lattice, then the distance between alpha over beta and z is less than 1 if and only if alpha minus, so like notice alpha over, divide this by beta, you've got rho over beta equals alpha over beta minus z, right? So if you think about that for a second, you can see alpha over beta minus z is equal to rho over beta, right? So this is less than 1 if and only if, jeez, all of a sudden hits me. Alpha minus mu beta. Oh, stink. Where's mu coming from? Mu equals to z, so so if I multiply this by beta, I get rho is alpha minus beta z. Remember, z equals mu. So alpha minus mu beta, that's this, is less than rho squared, beta squared. Beta squared, that should be... Sorry, guys. Oh, I'm having a... I don't know... Sorry, I'm just stuck on something here for the moment. In any event, the fact that you can choose these less than 1/2 implies that the distance between your closest Hurwitz integer and the point with the rational point that's actually given by the explicit division of alpha over beta, that's less than norm beta away from the where you need to be. In other words, the remainder is small enough. I'm sorry, I'm I don't think it's complicated. I'm not seeing it at the moment. I maybe have a letter wrong, or probably nothing. Probably just me. Anyway, so in 2 dimensions, we kind of have this picture. In 3 dimensions, we have this picture. In 4 dimensions, 1/2, 1/2, 1/2, 1/2. That's distance 1 because, 1/2 squared plus 1/2 squared plus 1/2 squared plus 1/2 squared is 1. So if these are perpendicular displacements, that's distance. But, so I said I guess they can't all be 1/2. Well, anyway, again, this is just a sketch, so I probably should have skipped it. My bad. Now I should warn you some more things about Hurwitz integers because they're dastardly. Since it's a non-commutative set like Quaternions, there's a difference between a right divisor. All right, so delta is a right divisor of alpha if alpha is gamma delta. But on the other hand, you could talk about a left divisor, and that would be alpha equals to delta gamma if delta was the left divisor. And just because you can do one doesn't mean you can do the other in the Quaternions. All right, and but anyway, he focuses on common right divisors. If alpha and beta have a common right divisor delta, then there exists gamma and epsilon such that alpha equal to gamma delta and beta equal to epsilon delta, and as such, you get that. And in summary, if the division of alpha and beta produces a quotient mu and remainder rho, then delta is a right divisor of alpha and beta. It's also a right divisor of the remainder, which means that the Euclidean algorithm works for the Hurwitz integers. All right, if you follow the right divisors, gotta be careful. Do all right divisors. Gotta be all right. I mean, all right. Oh, sorry, that doesn't usually work in my lectures. But, if we begin with alpha beta, you can follow the Euclidean algorithm using right divisors like such. Okay, anyway, I'm not really going to show you the details. I'm just telling you the Euclidean algorithm works if you take care to mind the non-commutativity. And in short, you can keep doing it, and eventually you get to a 0 remainder, right? And the one right before that, you can say is a right greatest common divisor of an alpha and beta, and by essentially the Bezout theorem for this thing, it's equal to a linear combination, a quaternion linear combination of mu and of mu alpha and nu beta. All right. So, yeah. And keep in mind, like it matters which side alpha and beta goes on doing this kind of thing. It's really picky. And so there's a prime divisor property of the Hurwitz integers. P is a real prime, and P divides alpha beta. Then P divides alpha or P divides beta. I sketch a proof of that right here. So it's from this right GCD thing. So if P does not divide alpha, then 1 could be taken to be the right GCD of P and alpha. And so there exists mu and nu in the Hurwitz such that mu P plus nu alpha equal to 1. So multiply that by beta, it gives you this. And I should say multiply by beta on the right. Multiply by beta on the left is something else, just like with matrix. And so then you've got P divides mu P beta. How do I know that? Oh, because it's got a P in there, and P can factor out to the whichever side it needs to go to. And P also divides alpha beta, because P divides alpha, right? And so, since it divides this and it divides that, it divides, excuse me, since it, oh, good grief, I can't use. What is alpha? Where's alpha beta? Mu P beta. I think I'm just supposed to say P divides. I don't think, yeah. I think this is a typo right here, okay? So the point is, P divides this, P divides that, therefore P must also divide that. So P divides, is it a typo? No, no, it was not a typo. I just can't remember. I'm an idiot. So why does P divide alpha beta? What's the statement here? P is a real prime. Oh, I'm an idiot. It's in the statement of a theorem. P divides alpha. So that's assumed here from the outset. So P divides alpha beta. Dummy. So then the point is, it divides this, therefore it divides that. Not I don't get that before a priori. So anyway, so since P divides this and P divides that in the right divisor sense, P must also divide beta, and we're done. Because in other words, we suppose that P did not divide alpha, it has to divide the other one. So modulo me muddling the proof, as seems to be my custom today, that should be very familiar. It's essentially how we proved the prime divisor property in our previous commutative life. I'll ignore that remark. Doesn't matter. So proof of the foursquare theorem. So here's the kind of main event, if you will. And it's got a few different moving parts, but let's get started here. First of all, you can write 1 and 2 as sums of four squares, right? And let's think about it. If n is composite, if it's the product of odd primes, then we have a and b are sums of 4 integer squares. Well, and if we have a and b are sums of 4 integer squares, then what? Well, then the foursquare identity gives us n as a sum of 4 squares. Right? So likewise, if it's a product of 3 things, I don't see what odd primes had to do with anything here. But if it's a product of 3 things, you can apply the foursquare identity to like a times bc, and then again with bc. So it follows that we just need to show this for all odd primes. The point is that 2, 2 is a product of 4 things, right? So if it's even, any number, it's either even times an odd, right? Or it's not even. So if it has composite, it's like odd times odd. So this covers all the bases, is the point, because of the foursquare identity. Allows us to take a product of 4 squares and rewrite it as product of 2 foursquare things, 2 sums of 4 squares, and let me just I keep saying it. Let me not say it. Let me just go back. Just give me a second here. I will find my way back to the formula. It's rather monstrous, as I mentioned, but come on. This thing, right? So we have 2 things that are sums of 4 squares, and multiply it out. You get a sum of 4 squares that's related, but in a somewhat complicated way to the given 2 sums of 4 squares. But there it is. Now, all right. So, long story short, it suffices to prove the foursquare theorem for the product of odd primes, because then from this paragraph right here we can build our way to any other integer, right? If it's composite in a more interesting way. So one of the critical moving parts here is called Lagrange's lemma. And Lagrange's lemma says this: if p is odd, then there exists L and M such that p divides 1 plus L squared plus M squared. All right. So, I don't think I'm actually going to go through the details here, but here's the proof. It's, arguments with congruences mod p, and, typical relations between like integers, and let's see if there's anything kind of sneaky. Let's see here. Anyway, there's the proof. You can dig into it if you want. I'm trying to keep the bigger picture here today, so I'm going to move on. All right. I'm really trying to focus more on the part that's about quaternions, is the larger point here. So the foursquare theorem is this, again, the sum of Any integer is the sum of four squares. All right, it's four integer squares for some a, b, c, d in the natural numbers and 0. Of course, this we've also been calling z plus at times, right? All right, so as we mentioned, 1 and 2 work, and if n is composite, and if a is equal to that and b is equal to that, right, then the foursquare identity says that n is also equal to the sum of four squares with c, where c1, c2, c3, and c4 are described by the foursquare identity, all right, as we just were looking at a second ago. Hence, n equals abc, which is a times bc, is also expressed as the sum of four squares, if a, b, and c are. So likewise, this applies to k factors by repeated application of this argument. So it suffices to show that p is an odd prime. If p is an odd prime, written as a sum of, thus it suffices to show that if p is an odd prime, it is written as the sum of four squares. All right, so we're going to try to show any odd prime can be written as the sum of four squares. So, all right. So, proposition 8, which was Lagrange's lemma, showed that p divides m squared plus l squared plus 1, all right, for some m and l integers. So you can factor, the thing is, and then now here's where the Quaternion magic comes in, right? Factor this thing in the Hurwitz integers like so. So you do 1 minus li minus mj and 1 plus li plus mj, right? Because you're thinking of this as being alpha conjugate times alpha, if you like. So, but p is prime, right? So it divides this, and so by the prime divisor property, it's either dividing this or that, right? So, so if I said if p was in fact not just a prime but also a Hurwitz prime, but p divides both, right? In fact, and so since it divides both, that means that there's some gamma such that gamma times p is equal to that, but that means that gamma is that dividing p, right? And there does not exist gamma in the Quaternion primes such gamma in the Quaternion primes is p is not equal to 2. Therefore, p is a prime but not a Hurwitz prime, all right? So suppose p was a Hurwitz prime. Oh, okay, so that's the thing. The earlier theorem, we supposed p was a prime but not a Hurwitz prime. That shows the sum of four squares, right? So we don't get to assume that the odd prime is automatically not a Hurwitz prime here, right? So suppose it is towards a contradiction. That's what this is, all right? But after the contradiction happens, then we realize, well, p is a prime but not a Hurwitz prime, and by our earlier work, that means p is a sum of four squares. There you go, four-square theorem. So we just take some time here to talk about like some history and what's going on here. So the two-square identity was discovered by Diophantus about 200 AD. He knew it. Certainly the Indian mathematicians also discovered it, you know, a little bit later, but not much later, and in several different places. And I think the Indian mathematicians also were aware of the four-square theorem, if I remember right. But I'll focus here on what I have written. So the again, Diophantus about 200 AD, and then Vete, I guess, I don't know, discovered geometric meaning in 1593. I'll show you that next page for the two-square identity. And then Coates, de Moivre, Gauss, Euler. You know, Euler had the e to the I theta is cosine theta plus I sine theta, right? And that really, I honestly, folks, like once you write that, you have in mind the complex plane. If you just realize, like, well, that's cosine comma sine theta. So I know some people say that like the complex plane and mapping complex numbers to the real plane to R2 was only discovered in like the mid-19th century, but I have a hard time believing that Euler was not already aware of the correspondence given the formulas he wrote. But whatever. And then Dedekind cleanly and elegantly used Gaussian integers to derive the identity and the related theorems. So the arguments by Dedekind are the ones that are found in Stillwell. We went a slightly different way since we followed Conrad's blurb, but it's all a lot of commonalities though. So just the two-square identity, let me talk about the geometric meaning for a second. So here's the geometric meaning. I don't think I talked about this before, but here's the geometric meaning. So the two-square identity is this. Excuse me, that right here, right? This times that is that. So the product of the sums of two squares is a sum of two squares. And you can understand that geometrically if you look at two triangles and then this triangle, all right? And you can look at the tangent of gamma, which is given in terms of the ratio of this opposite and adjacent. But then you can flip over to, tangent of theta 1 and theta 2, and as I do here. And let's see here. Sorry. Let me flip back out a little again here. So let's see the whole. So let's see here. So I'm looking at these triangles and this corresponding other triangle, which is related, but in a kind of funny way. Like the product of these lengths is its hypotenuse, and I'm saying that its adjacent side is that, and its opposite side is that. Studying the tangent of gamma, which of course is this, but then I'm converting it back to tangents of theta 1 and theta 2, like here. But then that you can write in terms of sine and cosine. So what I'm doing here is multiplying the top and the bottom by cosine theta 1, cosine theta 2 to convert this to cosine theta 1, sine theta 2, cosine theta 2, sine theta 1, cosine theta 1, cosine theta 2 from that, and then sine theta 1, sine theta 2 from that. But then, by ye old adding angles formula for sine and adding angles for cosine, we get sine of that over that, which says that the tangent of gamma, tangent of this triangle, is actually the tangent of theta 1 plus theta 2. In other words, this angle in here is aptly drawn. We've proved that the angle is theta 1 plus theta 2 by this argument. And so this is kind of neat. You've got two triangles, you've got another one that has the sum of the angles, and the lengths are related in this way. So this is some kind of geometric understanding, in some sense, of the two-square identity. The reason for that, how to say this, there's a little bit of a jump there. I'm not. Well, in any event, if you use complex exponential notation, a plus ib is, like h1 e to the I theta 1. a2 plus ib2 is h2 e to the I theta 2. When you multiply these two, you get h1, h2 e to the I theta 1 plus theta 2. And I'm sorry, guys, I don't know how to put this quite into words, but this is sort of the geometric underpinning of the Euler identity e to the I theta in terms of triangles, but it's clear as mud to me at the moment what the point of that is. So, but anyway, that is mentioned, like Viete discovered geometric meaning in 1593, and I said that this is it, but at the moment I'm not convinced. Why is it that? Oh, I see it. I see it now. I'm sorry, guys. So you have this triangle. So the Pythagorean theorem for this triangle gives you this. The Pythagorean theorem for that triangle gives you this. And the Pythagorean theorem for this triangle gives you that. Right? So, and the fact that this length times that length is built into it, right? So that gives you this times this equals that. That's the geometric meaning. This down here is digging further into the significance of the angles, and what it's revealing is that the angle of this new triangle is actually the sum of the angles of the previous two triangles, and that is really discovering the adding angles identity for the Euler exponential in a kind of sneaky, circuitous way. So, sorry I didn't see it immediately. All right, let's move on. So the foursquare identity, well, Euler probably started it in 1748. So I guess I'm saying that the Indian mathematicians didn't. I don't know. I wouldn't be surprised if I'm wrong about Euler starting it, but I don't know. In any event, Rodriguez in 1840 or so, said the product of rotations. The details are not in Stillwell as far as I see. So, I don't know. I can't tell what I'm saying there. Sorry, guys. Anyway, Hamilton discovered the Quaternions in 1843. He spent about a decade looking for a multiplication for 3 dimensions that would be much like the complex number multiplication for 2 dimensions. You see, complex numbers naturally implement rotations in the plane. So it's so natural to try to say, well, I should be able to take 3 dimensions and find rotations in R3 by adding some algebraic structure. It turns out that you can't. So finally, after like 10 years, Hamilton added another dimension and pretty quickly solved the problem, if I understand correctly. So searching for a multiplication in R3 with multiplicative norm property, that would imply the 3-square identity, which was already known not to exist by Legendre's older work, by the way. So if Hamilton had understood that, he wouldn't have been looking for it. But anyway, Hurwitz integers then were applied to give natural derivation of 4-square identities at the end of like the 19th century. So just a little bit of general math knowledge here for you. A normed division algebra is a vector space over the reals paired with multiplication, which satisfies that the norm of a product is a product of the norms. All right? And like usually we take norm of z as the length of z, but in number theory we square it to remove square roots and allow direct arguments, right? So here's a theorem. The only normed division algebras are the real numbers, the complex numbers, the Quaternions, and the octonions. This is you know, sometimes it's called Hurwitz theorem, actually. Hurwitz, only for n equals 1, 2, 4, and 8 does there exist an n-square identity. So in the original format of the course, I was going to prove this only norm division algebra's claim here, but we lost a couple days, so that had to go. Sorry, folks. But the proof is really just linear algebra, a couple pages of it. It's interesting, though. So either the reals, the complexes, the Quaternions, or the octonions. And the fact that this is the only ones that are out there, it actually reflects in a lot of higher math, because there's like ways of using these different multiplications on more abstract spaces of some dimensions but not others. So it is an important thing to know about. Quaternions and rotations. I will not speak of this. So anyway, hey, you get out of class early. What do you know? Anyway, hopefully I'll be back Wednesday, you guys, and I hope you found this interesting. If not, my apologies. I would rather have been there with you in person, but I'm still feeling rather off at the moment. So, thanks, guys.